Hello and welcome to another video about formal language theory. So in the last video we talked about how finite state transducers, which we introduced a couple videos ago, can be used to generate what are called regular relations. And in this video we're going to start introducing some properties of these things that can be generated using finite state transducers, which we will eventually put together into a definition of regular relations. This is just like what we did with regular languages when we were talking about the characteristics of regular grammars, or which are the same thing as finite state automata, that can be used to generate regular languages, except this time we're using FSTs to generate regular relations instead. All right, so property one, the empty set is a regular relation. This is very much like what we said when we said that an empty set is a regular language, but basically what this means is that we can define everything that we need to in such a way that it will produce an empty set, that your FST will produce an empty set. So essentially what we're going to do, just to give you an idea of how we're going to do this, is we're going to start with a start state, and maybe we have an end state, maybe we don't have an end state, right? But essentially all that's going to happen is that we can't access the end state ever, right? So we might be allowed to go around like this, like crazy, have so much fun here in our start state. We could go over here to this other state. We could go over here to this one too. We could go between these states, but as long as this final accept state is never accessible by our FST, we are not going to generate any relations, right? So that's essentially what we're going to do, but we have to create a formal definition of what this type of FST, what this type of transducer is going to do. All right, so the things that we need to define for a transducer, we need a start state, so we'll just label that start state S, because we don't really care what's in that start state. We have a set sigma, which is our set of symbols on the language that we're just recognizing, right? So we can think of this as the left side of each of the ordered pairs in our relation, right? This is going to be an empty set. We are not going to be generating, we don't recognize any languages, so we don't need to recognize any characters. The same thing for this one, which is the right side of each of our ordered pairs. This is the output language, right? Then we have a set K, which is all of our states. We have one state because we have to have a state specified there. So S is our only is our only state that we need to specify. F is a finite set of accept states. We don't need to have anything in there. We could have something in there if we wanted to. We could create 60 zillion states and just never get to any of our accept states if we wanted to. As long as this isn't accessible, then you're creating you're not recognizing anything, right? Because you never get to the state where you recognize it. And then we need delta, which is a set of rules. We don't have to do anything if we don't want to. We could create a bunch of rules that let us, mess around over in these states that are not accept states. We're not going to, because that's too complicated. So the world that we've created here in this sort of simplest way that we can create a grammar that generates a null set as the relation is just a start state. We don't recognize anything. Once we get to the start state, everything fails automatically, right? That's all that we've created is a start state. And this will generate a regular relation because that's what the definition requires. All right, so let's move on to the next property. The next property is going to be somewhat trickier to understand than this property. All right, so for the next property, the set containing A, for any A that is a member of sigma epsilon cross sigma epsilon cross sigma epsilon cross sigma epsilon, right? Sigma to the epsilon, right? Is an n-ary regular relation. So what do we mean by this? What is the first question we have to answer is what is this? What the heck is this symbol here, right? This symbol, sigma to the epsilon, is just a shorthand way of writing the union of your alphabet and the empty string. So if your alphabet is AB, then AB with this little superscript up here is just going to be AB empty string, right? That's all that this means, right? So what we're going to do is we're taking the cross product of your alphabet plus the empty string cross product with the alphabet and the empty string cross product with the alphabet and the empty string, right? So for example, if your alphabet was AB, alphabet empty string cross alphabet empty string is the same thing as AB empty string cross AB empty string. And when we say we're looking for A, that's a member of this cross this, right? We're looking for a member of this, and then we're going to put that in a set, right? So A is a member of this. This means we're looking for an ordered pair where we take the left member of the order from this set and the right member of the order from this set, and we make an ordered pair out of it. And any ordered pair like that, where you take one from one alphabet and one from another alphabet, if you put that in a set, then that is now a regular relation. Right, that's all that we're saying, is that any set with one ordered pair, essentially, is what we're saying. Any set with one ordered pair is going to make a regular relation. Right, so any of these would be a regular relation. Now, this definition actually says that you can make stuff that is much more than a pair, right? So you could be recognizing this set containing A, B, B, empty string, blah, 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 empty string. Right, you could be recognizing that, but all that matters is that you have only one relation, only one pair in your set. So what would a finite state transducer that recognizes this look like? Right, so imagine we are going to have to recognize something in this one. Unlike over here where we didn't have to recognize anything, we have to recognize just one thing here. Right, so that means that we have to be moving from a start state to an accept state, right? So we know that we have a start state and an accept state at least. If we only have to recognize one thing, though, we can just create only one arrow. This only one arrow, we recognize the string A and output the string B, right? So we give it one label. We label that one string. This is the only thing in our relation we have to recognize. So only if we feed in an A, we will end up here. It will output a B, right? That's how if we think about it this way, we're reading in an A. This moves us over here and outputs a B, right? So how do we, this is going to do this job, right? So it says anytime where you have only one rule, basically, you're going to recognize a binary relation. So how do we specify this? So K, remember that K is the set of all of our states. So we have two states in here, 0 and 1. We have a start state, which we've decided was 0. We have an alphabet for our left side, which is going to be A. Is the only thing in our alphabet on the left side. We have an alphabet for our right side, which is going to be B. We have an accept state in a set containing all of our accept states. We only have one accept state, and it's labeled 1. And then we have our set of rules, delta. So remember, we have a set. In this one, we take, if we're sitting in state 0 and we want to read in an A, right? This is how we start. We start 0. We want to read in an A. Then we're going to move to state 1 and output a B. Move to state 1 and output B. And we only have one rule, so we only have to have one member of this set. Now, since this is an ordered pair, we actually have to put another set of brackets around this, right? So this is our one rule is the ordered pair where the left member is 0, A, and the right member is 1, B, right? So this is how we do, this is how we show that anything like this is going to be something that you can produce with an FST. Right? You can use a finite state transducer to produce any set where you draw one member from one alphabet and the other member of the pair from another alphabet, and you have only one pair in it. All right, so these are going to end up being the base cases for our definition of the properties of relations. In the next video, we'll start looking at recursive cases.